Okay. Hi everyone, my name is Martin Cusino. I'm a software developer for Brainstorm. And in this tutorial, I'm going to introduce to you to our fiber viewer. This is a way to visualize connectivity results using white matter fiber visualization in Brainstorm. So recall that when you have projected your data from the sensor space to the source space, you will essentially have a recording, so a time series, at each of these intersections here. So at each of these vertices, these thousands of vertices, we now have a time series projected there. And so using connectivity, you will want to compute how each of these little source time series connect or are related to others, right? And so either you want to do this through all of your thousands of source time series, or either you want to group these time series together so as to make interpretation and also computation easier. And so maybe you'll group them together using atlases or regions of interest. In Brainstorm, we call them scouts. Let me select here, for example, the Mind-Boggle Atlas. And we see here that all of these intersections in this yellow region, for instance, will be grouped together. And this depends on the source or scout function that we choose. For example, here, this is the mean. So we'll just compute the mean of all these time series. Another recommended way to group or aggregate together different source time series can be a PCA. So it's up to you to see the best way. And so there are sort of two types of connectivity measures that you can compute. Here I dragged and dropped a source file into my process box. And if I go to run into the connectivity section of our processes, we see the different connectivity measures that we have available. We have a very simple correlation available. We also have coherence and more advanced measures such as phase locking value and so on. We have a tutorial page on that if you want more information. Notice here that we have sort of two versions of these processes for most of them. It's either a 1 by n process or a n by n. What this means is that if you choose the 1 by n, then it's going to do n number of comparisons, n being your number of regions, number of sources, depending on how you group things together. Essentially, you'll choose a specific region. For example, I will choose this yellow region here, and then I'll compute a correlation between this region and every other region. So I'm going to do a comparison of all of the regions versus this yellow one. So this is the 1 by n. And if you do an n by n, then you'll do a comparison, or rather, you'll do all different possible pairs of comparisons. So not only all region compared to the yellow one, but also you'll choose the second region being the red one, for example, then compute a connectivity measure to compare it to all other regions, and you'll repeat this iteratively until you have n times n comparisons. So this is much more computationally intensive, as you'll notice, and also much harder to interpret the results afterwards. So I won't compute it right now. I do recommend that when you do it, so I'll just select the n by n here, I do recommend that you group your sources into a specific region, right? Because otherwise you'll do 15,000 times 15,000 comparisons. It's huge and it will take forever to compute, and you might run out of memory even. So typically you'll either use one of the built-in atlases that you have with your template, or maybe imported from FreeSurfer. You can also compute your custom user scouts. I haven't created one here, but that's something that you can do using this display here, this visualization here. But let me just select this Mind-Boggle template, which is typically used for connectivity, and make sure that you compute a specific scout function on these regions. So you aggregate all of the sources, all of the sources of this, for example, yellow region into a single signal, right? And so you can choose how you aggregate them. You can do a mean, maximum, a PCA, and ensure you use before. That means that the signals will be aggregated before you compute connectivity. So that really makes sure that you don't have millions of comparisons if you just aggregate your sensors into, or your sources into, a subset of regions. So I've computed this basic correlation here. We saw that we chose 62 scouts, so we have 62 times 62 comparisons, not too crazy. And so let me close this display here and show you how we can visualize this correlation matrix here. So the basic way to see this is using an image. So if I click display as image, it will essentially show the connectivity matrix, right? So here both axes are the regions. So the diagonal is 0 because we're comparing the same region together. And just using my mouse, I can click a specific point. Here I click the point in the diagonal, and I see at the bottom what I have selected here. So I see that it's the same region that I'm comparing. So obviously we have a 0 correlation. And if I choose a point where there has some subcorrelation that is pretty high, so here it's there is an absolute value computed, so the values are between 0 and 1. We see that this had a pretty high correlation using based on our color map, and we see here that the value was 0.93, which is pretty high. And we see exactly which regions we are comparing here. So this is one way to visualize this. Of course, this is very basic. This is good for maybe a figure in your paper, but not so easy to interpret these results. So one way that we already had in Brainstorm is to use the graph viewer. So if you right-click on your correlation or connectivity result, you can choose to display as graph. And now we have all of our 62 regions plotted onto a circle. And so each of these labels is a specific region, and we see that we have different connections shown, but not all of them, right? And so you're free to use the display tab here to threshold as to select which connections are shown right now. So now the intensity threshold, so is basically all the connections that have a minimum correlation of this number is shown. So we have 0.88 here, so all the connections shown are greater than this. And as I play with the threshold, let me lower it a bit, you'll see that more and more connections are shown, right? And there are many ways to play around with this graph. You can filter by distance. As I increase the distance, shorter connections are now dropped because now I have a minimum distance of 35 millimeters, for example. And these are not meters, millimeters, of course. And another way to go through this graph is to have the option to only show connections that are between hemispheres, so connect either the left to right or right to left, exactly here, or also between lobes. So notice that these connections are grouped together based on lobes. So if I do between lobes, then only connections that are between different lobes are shown. And so there are many ways also to play around with this graph. You can select a specific node using these little dots in the middle here. So now I'm only showing connections that are relevant to this node. And now I'm showing all the connections. You can also select a specific region. Now I'm only showing connections that connect this specific region, and so on and so forth. So once again, this is maybe a better way from the connectivity matrix to go through and explore your data. However, it's a bit abstract, right? You only have labels here, and you have to sort of imagine where they are in the brain. So this is where fibers can really help us. So let me close this. And if we go to the anatomy tab and you right click on your subject, we now have a new option here called import fibers. And so what this does is it will let us import a fiber file that we have already extracted using another software. Could be MRTrix, could be DiPy, Diffusion Python Toolbox, could be anything you want. It will come from Diffusion MRI data, so you need to have this acquired already for your subject or your participant. And so the first thing that it prompts us is how many points we want per fibers. You can think of this as the resolution of your fibers. So the more points, the finer or the more detailed the fiber will look like in your visualization, but then also the more memory and the slower your display will be. So this is a trade-off. I think 100 is good. If things are really too slow for you, you can decrease it. And then you can choose a TRK or TrackVis file. I think this is really the most commonly used format in the diffusion community. If you think that another one would be helpful to be implemented, just let me know and I can add it. And now you will select either your subject's own fiber file that you have extracted yourself from another software, or you can also use a template. And we have this available. I'll show you at the end of this presentation where you can download it, where I computed 3,000 fiber files from a template brain, and I have aligned it to the ICBM template, which is a default template in Brainstorm. It's actually the anatomy that I've selected for my subject 1 here. And so they will be automatically aligned so that you can use it in your analysis. So let me just select this template track list file. It's going to quickly interpolate it to the number of points that you chose and then import it. We now have it imported here. Notice that it is in green, and that means that this is the fiber file that is selected for visualization when you plot fibers. But that also means that just like Cortex files, you can have multiple versions of your fiber file, maybe a different tractography algorithm, maybe more lower, higher resolution. So feel free to import many, but only the one selected in green. So if you just double click on the new one, it will select it, will be the one used for visualization. And if I double click here, I will display in 3D the fiber files. And here are our 3,000 files that I have extracted from my template. Notice that most common pathways are represented here. And just to show you that it is aligned to the rest of the anatomy, if I go to the surface tab, I can add other types of surfaces. Let me add a Cortex file here. Let me add just some transparency so that you can see, and also let me remove the atlas. So no more atlas. Let me add transparency to the Cortex. Great. And now you see the fiber files inside the Cortex, and you can see that they are properly aligned. And so when I use the fiber viewer, fiber display, which I'm about to show you, these are where the fibers are coming from. They're coming from this selected file here. So let me close this and go back to our connectivity file. I believe it's under raw here and under my source file. Great, here's my correlation. And now that I have imported a fiber file for this subject, when I right click on my correlation file, I have a new option here to display fibers. So I'll go ahead and select that and explain to you how it works. So this is a bit small in a single screen setting. So let me just move my Brainstorm window a bit to the left. I'll only use the display tab for thresholding. Let me move my 3D visualization here and increase the size of my graph viewer because this is the busiest figure here. So we really recommend that you use 2 screens for this. It will probably be much easier. And so here on the right, I have the graph viewer that I've introduced to you earlier in the talk. And on the left, I have the display tab that I've used before. And just like before, I can play with for example, the intensity threshold to show connections with higher or rather lower correlation. And notice that as I play with my threshold here, both the graph viewer and the fiber viewer are updated. So these 2 figures are now linked. And essentially all of the connections that pass our threshold and that are shown on our graph viewer on the right, if they have an associated fiber, so in my fiber file that I just imported, if there is a fiber that connects, for example, this very specific region, the insula, to this other region here, it will be shown, we see it here, it will be shown in my fiber viewer as well. So since these figures are linked, you can really see where the connection shown in the graph right now is in the brain. And so obviously now I have only selected a single region, but this really helps as you plot more and more regions. Notice that the color bar is a link between the 2 figures. So fibers that are more green in the fiber viewer are also connections that are greener. Also, you can interpret this as a lower correlation measure right here. And obviously all of the previously introduced display options also work. Oops. So for example, the distance filtering, as I increase it, short fibers are gone. If I restrict to only showing connections between hemispheres, we see that fibers that did not go across both hemispheres are now gone. Similarly for between lobes. And finally, we have one new option, which is to show connections that are either anatomically accurate or anatomically inaccurate. I have to put some asterisks or some quotation marks here. So this anatomically accurate terms is really based on your fiber file. So here we only had 3,000 fibers. This is a bit short, a bit small. So obviously not all the fibers in the brain are represented. So this is a little asterisk that you have to keep in mind when you interpret your results. But essentially what it means is that if I click, for example, anatomically accurate, notice the graph viewer will be updated and much less connections are now shown on the graph viewer. And essentially the connections that are hidden are connections that did not have an associated fiber. Connection between regions that did not have a fiber in the fiber file that connected these two regions anatomically are now gone. So this is why we call it anatomically accurate. But of course, this is really based on the size and the correctness of your fiber file. So be careful in your interpretation, but this can help you. And similarly, if I do anatomically inaccurate, now no fibers are shown because there was no fiber shown for no associated fiber found for these connections. So now here on the right, we have all the connections that have a correlation coefficient that is higher than 0.78. So it's a good correlation, strong correlation, but they did not have a fiber associated with them. So of course, this assumes that the fiber file is perfect, which it is not, and it's a small one in our case. But assuming that it would be perfect, maybe you could interpret this result as, for example, oh, maybe this connection is not direct, right? It doesn't go directly from this region to the next, but rather goes through an intermediate regions or uses two different pathways, two different fibers that are that connect sort of the same intermediate result, so that the same intermediate region, so that it goes through different regions at once. So you can interpret this like this. Great. So this was a short introduction to our fiber display. If I close this and I show you our tutorial page, let me just go back to the Brainstorm tutorial page here. If you want to try it on your own or download our fiber template, just search for the fiber virtual fibers for connectivity tutorial page here. And if you click on it, I have written a short introduction that basically shows you all the steps that I have done today to import the fibers and to plot them. And if you do not have your own fiber file, we have the template fiber file that I was talking to you about, that is aligned to the ICBN template. So that means that if you just project your subjects to this template in Brainstorm, you can just import this template file and then play around with the fiber viewer, even though you do not have your own fiber file for your own subjects. You do not have white matter diffusion acquisition, or you did not compute your tractography yourself. Okay, thank you very much for your time, and let me know if you have any suggestions or questions.